This will be all right. I have a pleasure to introduce the first speaker of the morning session, Professor Piotr Nowak from IMPAN, and he will talk on the computing cohomology with via semi-defined programs.
Thank you very much. I would like to start by thanking the organizers for the invitation to this excellent conference. So I would like to speak about cohomology of groups and computing this cohomology in certain cases. Just a brief reminder. So I'll start with a gentle introduction or a survey of a property called property T, which I will be interested in. So the setup in general will be that of locally compact groups, but more specifically discrete finally generated groups. So of particular interest will be groups given by finite presentations. So you can see examples here, but also lattices in certain topological groups. So lattices in Lie groups like SLN Z sitting in SLN R. Okay, so these are just some examples that will be of interest here. So the property of groups that I will be interested in is called property T, and it's a rigidity property for groups. So here is the definition. So property T has a lot of different characterizations, and this is one of the reasons why it's a very useful and powerful property. And here's the one that requires the least technicality. So a group has property T if whenever it acts by affine isometries on a Hilbert space, there is a fixed point. Okay, so right away, this is the same as saying that the first cohomology of the group with coefficients in a unitary representation vanishes. Coefficients in a unitary representations, I mean, you take a G module consisting of a Hilbert space with the G module structure given by this representation. Okay, and this is immediate because one co-cycles for such G modules are exactly affine isometric actions, and co-boundaries are exactly the actions that have a fixed point. So this is very easy. Once you write it, it's 2 lines to notice this. Okay, so here are some examples of groups that do not have this property. So most groups will not have this property. So here's Z acts on R by translations. There's no fixed point. There's no property T. The same works for all finitely generated abelian groups. And another example is that that of the free group, which acts on an infinite dimensional Hilbert space, roughly speaking, in such a manner that whenever you extend a word by the next letter, you shift by one in the new direction. You have infinitely many of those, so there's no problem. Okay, so both of these do not have property T. So this property was introduced by Kazhdan. So I'll give some examples shortly. So property T was introduced by Kazhdan in 1967, and originally he used a different definition, which is the following. So he looked at the space which is called the unitary dual. So this is the space of equivalence classes of irreducible unitary representations. There's a certain topology on it, which is called the Feld topology. And the property is defined in terms of the trivial representation being an isolated point. Okay, and he proved, he gave the first example, and he said, he proved that SLNR, and in particular lattices in SLNR, so SL and Z, and in general higher rank lattices and higher rank Lie groups, so for here for n greater or equal than 3, that these have property T, right? So starting from SL3, these groups have property T. SL2 does not have property T, which is again easy to see because SL2 has a finite index subgroup which is free, and property T passes through finite index subgroups. Okay, so why should we care about this property? So the one of the most important motivations are expander graphs. So what are these graphs? So consider a finite graph, and what I can look at is for any subset of the vertex set, I can look at its edge boundary. Okay, so these are all the edges that connect the vertices in my sets to the complements. Okay, so if this is my set, then this will be the edge boundary. So this is of course motivated. So there's a notion of the Cheeger constant, which is motivated by a similar notion coming from manifolds, and this is a constant which measures, so you minimize the ratio of the size of the boundary relative to the size of the set. Okay, so basically, what's the smallest boundary in your what are you're looking for the smallest ratio of the size of the boundary to the size of the set in such a graph. So this is a measure, and sometimes it's actually called algebraic connectivity, but it measures how connected the graph is, right? So how for any given set, how large is the set of edges that connects it to the complement. Okay, so this is, of course, this is a positive constant for any finite graph. However, what we are interested in when we're talking about expanders is in an infinite family of finite graphs. And what we would like to have is that this number for all of these is uniformly bounded away from 0. Okay, so if you're looking for graphs that are highly connected, then of course complete graphs on n vertices are such examples. The problem here, of course, is that the degree grows. So what we would like to have is we would like to have families of graphs with large connectivity but bounded degree. Okay, so this is what expanders are. So informally, so these are families of increasingly larger graphs of bounded degree in which all sets have uniformly large boundaries. And here's the definition, a formal definition. So these Cheeger constants have to be greater than equal than some uniform constant, positive uniform constant C. The degrees are uniformly bounded and the number of vertices grows to infinity. Okay, so why these graphs are useful? Why are these graphs useful? So first of all, the obvious thing is that they are useful for designing any kind of a robust network, right? So whether it's a computer network or I don't know, some logistic plan or whatever kind of network you need. These have a lot of good properties, so it's difficult to these graphs have the property that it's difficult to disconnect them, right? They are highly connected, and yet at every vertex you limit the number of connections. So this is one obvious application. There are many applications in theoretical computer science. So here's a screenshot from Twitter. This is taken 18 minutes after the I think it was the first royal baby was announced. And Twitter has this feature on the side here, which is called trends. So it shows you what is trending. So the algorithm that's responsible for creating these trends is called the streaming algorithm. And the way that these streaming algorithms work is that they look at a large stream of data, okay, and it's sort of a gate through which the stream passes, and each piece of data is seen only once. And based on this, the algorithm is supposed to pick up what's important, okay? So as you can imagine, so Twitter has to do this in real time. And you can imagine that that this stream of data is enormous, right? So every second there are millions, if not more, words that pass through this algorithm. And so so one application of expanders that you can that exist is that the fastest or the optimal algorithms for doing this, so these streaming algorithms, are actually designed using expanders. So so this is an article about this from the Quanta magazine. The idea is, roughly speaking, that that you chop up the words that appear into smaller pieces and then use expanders to reconnect them. Okay. All right. So this is why you would care about these graphs. However, the problem is that they are difficult to construct. So their existence was known since the 50s, and it was an open problem how to actually give an explicit construction. And there was a theorem in 1977 by Margulis, who noticed that if you take a finitely generated group with property T, and if you assume it is residually finite, so there exists a sequence of finite index normal subgroups in it that are getting less and less dense in a way. So the indices grow of these, the indices of these subgroups grow, and then the intersection is trivial. And if you take the sequence of Cayley graphs of the quotients, then these form a sequence of expanders. Okay, and the reason for this is exactly property T. So the fact that the group G has property T is responsible for the fact that these are expanders. Okay, so if you want an explicit example now, you take SL3Z and you take the subgroups SL3 PI Z, where P is a prime, and the Cayley graphs of the quotients. These are just matrix groups. So these are your explicit examples of expanders. Okay, so there are some other applications which are purely theoretical. I'll list a few of them. So one is local rigidity theorem due to David Fisher and Margulis. So they showed, maybe I should say that in general, whenever a group has property T, property T implies various rigidity statements for objects associated to the group. So for group actions or group algebras or things like that. So here's an example. So this is a local rigidity theorem, as it is called, and you start with a group that has property T. It acts smoothly on a smooth manifold. And then you take an action on the same manifold that's also smooth, that's of the same group, that's close to it, to the original one. If it's sufficiently close, they actually have to be conjugates. Okay, so this is a very strong statement. And the reason for it is property T. The second application is to Baum-Kohn type conjectures. So the Baum-Kohn conjecture, whenever it's true, it's a vast generalization of the Atiyah-Singer index theorem. And I won't state the formulation here, the index map. So it's a certain index map from the K homology of a certain classifying space to the K theory of a certain C-star algebra associated to the group. And so there are counterexamples. The conjecture is still open, but there are counterexamples to certain versions of this conjecture. And the only reason for these, the only source of these counterexamples is again property T, because once you have property T, you can construct certain projections and certain C-star algebras. Projections are non-commutative bundles, so they give rise to K3 classes, and these K3 classes tend to not lie in the image of the appropriate Baum-Kohn assembly map, while the conjecture would imply the map should be surjective. So this is how you can do this. And then there is also a rigidity program for operator algebras. So this was started by Alain Kohn, but really it took off with results of Sorin Popa. And so basically you start with the group ring or the group algebra. You complete it to a von Neumann algebra, so you close it in the weak topology in B of H in the operators on the Hilbert space. You get a von Neumann algebra, and you ask how much of the group does the von Neumann algebra remember. So if two algebras are isomorphic, are the groups isomorphic, and so on. Okay, so this is so again in this setting, property T is crucial for proving these results. Okay, so once we know why is this property interesting, what are examples of groups that have this property? So there's not that many, and it's usually difficult to show that a group has property T. So finite groups have property T. This is easy to see, right? So if I have, it's easy to see from the first definition I gave. So with the cohomology or with the affine actions, because once you have an affine action by isometries of a finite group, you can average the action or the orbit, and that's your fixed point. And then there are essentially three classes of infinite groups with property T. So in a way, property T is a form of compactness for the group in the right setting, right? So that's why finite groups having it are sort of, even though it's trivial, it should be seen as some sort of motivation. So the classical examples are the high rank simple Lie groups and their lattices due to Kazhdan originally. Then in the middle of the 90s, there was a new method. Maybe I should say that, so what Kazhdan uses the algebraic structure of the Lie group together with the knowledge of the representation theory of the Lie group, because in those cases, you actually do know a little bit more about both the structure of the group and the representation. So that's what he used. Then in the middle of the 90s, there was a second wave of examples, and these are automorphism groups of certain buildings, so-called thick buildings. So buildings are simplicial complexes which have a lot of high-dimensional branching. Okay, so for instance, these A2 tilde buildings, you can visualize them as planes triangulated, and every edge you have another triangle and another plane sticking out. And you continue this to infinity. So there was another method, so-called spectral geometric method, that was used to prove that these groups, the automorphism groups of these simplicial complexes, have property T. And then there are certain random groups. So Gromov came up with a model in which you can say what is a random group. So you choose generators or relations, well, in general, relations at random, and then it gives you a model of what one can call a random group, and then you can measure which properties are satisfied with what kind of probability. And so in Gromov's model, some of these groups, depending on the parameters involved in that model, they do also have property T. Okay, so what I would like to discuss is a new family of groups with property T and a new method of proving it, and the method will involve semi-definite programming. So the family of groups I'll be interested in is the family of automorphism groups of free groups. So you start with the free group of n generators. Odd Fn will be the group of automorphisms of Fn, so isomorphisms from Fn to Fn, and the inner ones are the ones given by conjugating by a fixed element. And then there are also the outer automorphism groups, the outer automorphisms. So this is the out Fn, which is odd Fn divided by all the inners. Okay, so it turns out that in geometric group theory there is a certain setting or an analogy between three classes of groups, and this is a very influential analogy that people use to study two of these families. So basically we have mapping class groups of surfaces, linear groups, and these outer automorphism groups of free groups. These three classes are thought of as being similar, and the reason for this is this isomorphism that happens for n equal to 2. So out of 2 is the same as GL2Z, which is the same as the mapping class group of the torus. Okay, so a very important theme in geometric group theory is to take certain results that are classical for linear groups, for instance, the Tits alternative or something similarly important. And so we know that that is true for linear groups, and then try to prove it for either out of 2, out of n, odd of n, or mapping class groups. Okay, so this analogy is responsible for a lot of results, and it's quite influential. And an actual question in this setting that's been open for a while is, do odd Fn or out of n have property T? The same question applies to mapping class groups, but at this point nothing is known about that. Okay, so the answer is so in the case of SLNs, it was the property starts with n equal to 3. So there's a certain point at which there is a transition. Right? So here it was known for a long time that also for low indices, nothing similar to property T could be true. The first for n equal to 2, odd F2 surjects onto out of 2, and out of 2 is GL2Z. Property T passes on to quotients, which is easy to prove. We know that GL2Z does not have property T. So here it was negative, and it was also negative for n equal to 3. And this was a theorem of McCool in a completely different setting. So he was just computing homology, and he showed that the homology, the first homology of odd of 3 is non-trivial. So it has infinite abelianization. And that implies there is no property. Yeah. Okay, so the higher cases were all open, at least since the early 90s, which is the first time I think this appeared in print. So this was in Alex Lubotsky's book from '94. I think he mentioned this as an open question. So the theorems that I'd like to present are answers to this problem. So the first one is with Marek Kaluba and Takaozawa, odd of 5 has property T. So this was the starting point. And then with Marek and David Kielak, we proved that odd of n has property T for n greater or equal than 6. Okay, so let me try to explain how does this work. So the first important thing is that we will work with a certain subgroup of odd of n, which is the subgroup generated by Nielsen transformation. So this is the special automorphism group of Fn. And the Nielsen transformations are written here explicitly. So they are indexed by I and j, and its multiplication by an appropriate fixed generator, either on the left or on the right, with either in positive or either by the generator or by its inverse. Okay, the way that one should think about these is these are the non-commutative versions of row and column operations. Okay, because there is another equivalent definition, which is as follows. So we have the map from the free group to z to the power n. This is just the Abelianization, which induces a map from autofen to GLN. And then inside here, I have a copy of SLN. And the subgroup I'm looking at is the pre-image of SLN under this map. Okay, so this is what's important is that this subgroup has index 2 in autofen. And as I said, property T passes through finite index subgroups. So we can just as well work with this, and we'll get property T for autofen. Okay, so let me describe the new method of proving property T. So it started with the result of Takaozawa in 2014, and here's how it works. So we start with the group ring, and inside the group ring we have the Laplacian. So inside the real group ring, we will be working with the real group ring. So there is the Laplacian element, and it's just defined as this is a non-normalized one. So it's just the number of elements in the generating set, which is denoted here by S, minus the sum of the generators. Okay, so this is a discrete version of the Laplace operator. And so what Taka proved is he proved that you can actually use this element inside the group ring to characterize property T. So he showed that a group with the generating set S has property T if there is a positive constant lambda and a finite collection of elements from the group ring such that delta squared minus lambda delta is a sum of squares of these psi i's. Okay, so so this was very surprising because it says that property T can be verified in finitely many dimensions. So in principle, this property that has so many applications and can tell you about vanishing of cohomology or rigidity properties for group actions, for group algebras, it turns out that all you need to check this for this property actually happens on a finite subset of the group. Okay, so this was quite surprising. So in Taka's original paper, he already, I think even in the abstract, he suggested that perhaps this opens the possibility to try to prove property T for classes, for new classes of groups using computer-assisted methods. And this is exactly what we're going to do. So so how should we go about this? Okay, so let's start with this sum of squares. So if I have an element eta, which is a sum of squares, I would like to be able to translate it somehow. And okay, so I'm going to assume there's a finite subset such that all of these psi i's are supported on the subset E. Okay, and in everything that I'll be doing later, this subset always will be the ball of radius 2 in the group. Okay, and it's easy to notice that eta being a sum of squares is the same. You can rewrite this in the form of in the following form, that you first choose, take up the elements, enumerate the elements in the set E, the group elements, so these form the basis. And the condition becomes that B transpose, where P is a certain positive definite matrix, is equal to eta. And the reason is that, well, you can take the square root of P, and then you can rewrite this whole equation in this form. And in this setting, the coefficients of Q will simply become, the columns of Q will become the coefficients of the ith column of Q will become the coefficients of the particular psi I. Okay, so now we have a translation of this notion into something that involves positive definite matrices. Okay, so now the idea is to try to find the matrix P using a semi-definite solver. Okay, so we fix. The way it works is we fix a set in the group, and we try to find. We try to ask the solver to look for the matrix P on the given prescribed set, and then it might work. It might not work. It might happen that in principle it might happen that that one needs a larger set that we're not able to access, for instance, because it's too large. So what are the issues that one runs into here? So the first issue that in this particular group one can run into is that the ball of radius 2 in SOF5 has 4,600 elements, actually a little bit more. However, the thing is that this means that the matrix has over 11 million variables, which is far too large for any of these solvers to work with. Okay, so there's a way around it, and I think Marek in his talk later today will describe this in greater detail. There is a way to symmetrize this problem and reduce the number of variables. Okay, so first of all, we can take a certain finite group that acts on the ball of radius 2 in S out of 5, and it turns out that the whole problem can be considered to be invariant under the action of this group. Okay, so this is just done by averaging, because the group is finite. So then once you do this, you average the problem, but then you end up with matrices that are invariant with respect to some kind of group action, right? So these are matrices which are indexed by the sets E, so by the ball of radius 2, and they will be constant on the matrix, on the orbits of the action of that finite group. Okay, so no solver can work with group invariant matrices once, especially that this, we cooked up this group and the group action for the particular problem we needed. So there's no solver that can work with such restrictions. However, there is another theorem that we can use, a classical theorem, which is the Wedderburn decomposition. And it turns out that the algebra of these gamma invariant matrices, where gamma is this finite subgroup, can be written as a direct sum of just matrix elements. Okay, so this is a classical thing. So one thing that is needed here is so we need this isomorphism here to be explicit, because in the computation we actually need to go back and forth between the two forms. So the invariant one and the block matrices. So this can again be done. So in the end, so you do this, and in the end, the solver gives a positive definite matrix and some number such that this equation that that we wanted to solve is solved. However, the problem is that this is, of course, a numerical solution, right? So we were looking for proof. So far, we only have an approximation. It's a pretty good approximation. The numbers the accuracy was to the order of the order of 10 to the minus 10, but still, it's just an approximation. However, there is a little bit of magic that happens here, and there's a lemma that goes back to, again, Taka's first paper, and then it was quantified by Nenzer and Tom. And it says that this Laplacian, if you view it inside the augmentation ideal, so it's an element in the augmentation ideal. If you look at the augmentation ideal and you look at self-adjoint elements inside the augmentation ideal, then for those elements, the Laplacian is an order unit, which means that if you have a self-adjoint element in the augmentation ideal, if you add a sufficiently large multiple of the identity of the Laplacian, then the sum becomes a sum of squares. So this is similar to how identity behaves for matrices or operators. If you have a self-adjoint matrix operator, then the spectrum is in the real line, and if you add a sufficiently large multiple of the identity, you get a positive one, right? So so this is the same, but it's happening inside the augmentation ideal, and instead of the identity, we're using the Laplacian. Okay, so this is the same phenomenon. And there is also an estimate of what R do you actually need? What's the smallest R that suffices? Okay, and it depends on the L1 norm of this eta and on the support, on the size of the support. Okay, so how do you actually turn this into a proof now? So we have the approximate solution. I can rewrite this, right? So here nothing happened. I just added 0, right? But here I have the error. I know that this is positive, and here I have the error, right? So now to this part, I want to apply the lemma and maybe add some multiple of the Laplacian to see if I can turn this side to be this element to be positive. Okay, so I add epsilon times delta, and this epsilon will depend on this estimate here. And then this becomes a sum of squares. This is a sum of squares by definition. And here what I get is I get kappa minus this epsilon. So if kappa minus epsilon is still positive, then it's all fine, right? So then I still have solved my equation because I didn't really care about the constant. And I have the proof. So the idea here is basically that if I have an approximate solution and this epsilon, so the epsilon measures how large is the error, and if the epsilon, so if the solution is sufficiently accurate, and I can make this epsilon sufficiently small and the kappa is sufficiently large with respect to this epsilon, then I'll get that next to the approximate solution, I have the existence of a true solution. Okay, so this is actually how it worked. So data from the solver was the matrix P, lambda was 1.3. Here was the estimate on the L1 norm, and it's important. I didn't mention this before, but it is important that the L1 norm here is computed in interval arithmetic. Okay, so this is what gives a rigorous proof here. Yeah, so basically we have this epsilon that we need to choose, or this R that we need to choose, is 1.2, sufficiently small that we easily get a positive constant where we need it. Okay, so this is this process I think Marek will explain in more detail in his talk. And okay, so I would like to say a few words about how the general case is done, because okay, so with this method, one can obviously do case by case, right? So you take a group, you apply this procedure, and then you either get the answer or you don't. However, what we have is we have an infinite family of groups, right? So indexed by the natural numbers. And the question is, how can you actually prove it for the whole family if you're able to just do finitely many computations? So so maybe I'll just go over this fairly briefly. The proof works for both classes of groups, for S out of n, but also for S out of Z. So these are generated either by Nielsen transformations or the elementary matrices. Okay, and these have both families have a very nice structure where they form a tower of inclusions, where you just add a generator to the base group, right? So you either take Z to the power, to the next power, so this should be Z to the power n inside Z to the power n plus 1. So you extend by the next generator, either with the free group or with the free abelian group. And then what I want to do is I want to look at a simplex. So these generators are indexed by pairs of numbers from the set 1 through n. And I'll use a simplex to visualize what's being used, what's happening here. But basically what I would like to do is, in the simplex, the edges are, so I span a simplex on 1 through n, and the edges are given by pairs of points. And I would like to assign to a given edge, I will assign all the generators that have those two indices. Okay, so here's a picture which will be much more informative. Okay, so this is for 4. So here I have edge given by 2 and 3, by the numbers 2 and 3, and I have a copy of either S out of 2 or SL2, depending on which family I'm looking at. And this is generated inside S out of 4 by all the elements with indices, all the generators with indices 2 and 3. Okay, and I also have the same for I have the same for every edge. And also I have so I have the Laplacian for the whole group, but I also have the Laplacian for the subgroup, right? So to each edge, I have a small Laplacian for the subgroup associated. And so there will be different situations depending on whether how these edges are positioned. And it's an important property that if the edges are in the position that we see here, so they're opposite, so they don't share any vertices, then the corresponding copies of S out of 2 commute. Okay, so the generators commute. Okay. Okay, so if I start with the Laplacian inside for my group S out of n, then I have these Laplacians for each edge. I also have the action of the alternating group. So the alternating group simply permutes the vertices, and it also permutes the copies of the Laplacian. Okay, so the key thing is to now decompose the Laplacian in S out of n into smaller pieces that are coming from the edges. So the first statement is that the Laplacian in S out of n decomposes as a sum of the Laplacians over the edges. But you can also just fix one of the edges, use the action of the alternating group that permutes them, and just write it in this form. So it's simply the normalized orbit, the sum over the normalized orbit. Okay, so this is good, but we know that S odd F2 or SL2 do not have property T, so we cannot really use those Laplacians that are attached to the edges because they come from SL2 and S odd F2. So what we should really do is relate the Laplacian on the level M to the Laplacian on the level N, right? And this is what happens because each one we can write using this formula, then we can also relate the two on any different two levels, M and N, okay? And these are the formulas. And the general idea is that we will now decompose essentially the whole equation here in this fashion, that we will relate the equation on the level M to the equation on the level M, and knowing the solution on one level, we'll get the solution on any higher level. Okay, so this was for the Laplacian. Now we also need the Laplacian squared, and the Laplacian squared, this is the formula, and it's this is over the sum of products over the edges. And then we have three different situations. So they either it's the same edge, or they're adjacent, or they're opposite. So we get three different parts here: the square part, the adjacent part, and the opposite part. And the square part and the opposite part are immediately are automatically sums of squares. So for the squares, it's easy, it's obvious. And for the opposite part, it follows from the commutation, right? So the opposite part consists of products of Laplacian for edges that don't have any vertices in common. So the corresponding copies commute. And you can just rewrite elements like this, which give you the Laplacian, and you can switch them around, and then you get sums of squares. So this means that the whole issue is inside the adjacent part. And maybe I'm running out of time, so I'll just say that there are formulas that relate all of these. So the adjacent part on the level M to the adjacent part on the level M, and so also for the opposite part. And the main technical theorem is that if I have the adjacent part, if I can prove positivity of a certain element at a level N, then under certain assumptions I can get positivity for infinitely many levels from some point on. Just by applying these formulas that decompose our equation into smaller pieces. Yeah, so maybe I won't get into this further. This is the general idea. Maybe the one thing I would like to mention is that a specific application of property T for odd Fn is to the product replacement algorithm. So the product replacement algorithm is an algorithm that was created in the 90s. So it's an algorithm that produces, once you have a finite group, it produces uniformly distributed elements within that finite group. So this is implemented in GAP, and it's used. It's widely used. So the interesting issue when it was implemented was that it turned out to work extremely efficiently. So very quickly you would get to a uniform distribution. Okay, so it was unknown why this is the case. So in 2001, Lubotsky and Pak showed that the explanation would be property T for odd Fn. And the reason is that they noticed that the algorithm, the way that it works, it's actually implemented by a random walk of odd Fn on a finite group. Okay, so if you have property T, there is a uniform estimate on how these random walks converge to the uniform distribution. Okay, and so this is what they proved, and so one of the consequences of property T for odd Fn is that now this is explained. This explanation actually holds. And the last thing is that there's also work that we're doing in higher cohomology, where we use similar methods and semi-definite programming to show vanishing of higher cohomology. So we generalized this the sum of squares approach to higher cohomology, and Piotr Mizerka yesterday or 2 days ago gave a talk on some results that we have for this with this for SL3Z. All right, I'll stop here. Thank you.
Any questions? Remarks?
So there is a proof by Martin Nietzsche. So he's a postdoc of Andreas Thom. So he has he has a preprint with the case Auto 4, and he shows that it's that it does have property T. The point is that he needed to go outside of the ball of radius 2. We were not able to. So he went a little bit outside. So you need actually a larger step.
So that in your algorithm, you could just somehow prove that the group has a property. That, could you, for instance, show that it doesn't have?
No, that's more difficult because then you need to exclude all the lambdas, right? So you have the equation delta squared minus lambda delta, and lambda can be any positive constant. So you will need a method of excluding any positive constant, which I thought about it. I don't see a good way at this point of approaching.
And could you guess maybe there are some, let's say, geometric properties of these groups, just you know, somehow that you can guess that the group intuitively, that the group has a property T or it does?
No, I would say it's quite difficult to
just in terms of ideal boundary or something.
No, so for instance, so hyperbolic groups. Yeah, among them there are groups that don't have property T and ones that do have property. So it's quite difficult to somehow estimate which ones should have it.
This was my question.
Yeah, so there are known hyperbolic groups which do have it. So it's not easy to construct them, right? So there is it's a limiting process. So you have to take infinitely many quotients, and in the limit you get a hyperbolic group that has property T. But on the other hand, you have the free group, which is hyperbolic and it doesn't have property T. So again, it's and some of these random groups in the Gromov model, they are hyperbolic and they have property. It's very difficult to say.
So that there is no, let's say, just intuitively.
No, other than some like this analogy between SLN and vamping class groups or an autofan. This was one way of sort of estimating which groups should have it. Yeah. But that's about it.
Okay, thank you very much.
Thank you.
Any more questions?
Where does the name come from?
Property T. So it comes from the definition, original definition of Kazan. So T is the trivial representation, and the parentheses should depict that it's the trivial representation is isolated in the delta topology.
Okay, thank you very much.
Thank you.
And we'll be see you in 5 minutes. You have a choke.
Let me set up the stream for you. And, yeah, screen is not needed.
Probably.